Thank you. So to start off, I'll just introduce myself. My name's Sam. I'm a developer advocate and former developer for SEML. Worked on LGTM.com for a good number of years. I've been passionate about open source and security in particular for a number of years now. Used to be a contributor to Signal Android and desktop, so yeah, that was what I spent most of my evenings doing for at least 6 months. It was kind of fun. And that's my Twitter handle. That'll be on every slide, so you can, if you take a picture of something and you want to follow me later, you can do that. So I'm going to start off today with a story. It's a story of many bugs. So back on the 7th of September 2017, my coworker Mo found and disclosed a vulnerability in the Spring framework. Now this particular vulnerability made use of what was called the Spring expression language, which allows you to effectively run arbitrary Java code from strings that you can pass in. Now in this particular instance, they were interpreting some HTTP headers as Spring expressions, which then meant that anyone that could send a specific HTTP request to a Spring server would be able to get remote code execution on that server. So pretty severe. So he reported the vulnerability, and then on the 21st of September, Pivotal published a patch that fixed the vulnerability and then made a public announcement to let everyone know that they should update. Well, it turns out that the patch didn't work. On the 22nd of September, Mo went and checked the patch, saw that it was still vulnerable, and sent a new exploit that used a slightly different execution path that was still a remote code execution. He sent that to Pivotal. Then on the 26th of September, Pivotal sent Mo the details of how they were planning to fix it, so that he could check this time before they went public whether or not the fix was complete. Turned out the fix wasn't complete. It was still vulnerable to effectively the same kind of mistake that they were making. So in the end, on the 25th of October, they actually published a complete refactoring of the code that was affected and continuously vulnerable, because they realized that they were unable to prevent more of these happening, and they had to go about it a different way. Let's look at a slightly different story. It's also a story of many bugs. So on the 27th of April 2016, Apache Struts announced an RCE which had a very similar kind of behavior. They had an expression language called OGNL that allows you to access arbitrary Java objects, and you could use that to run arbitrary code. So in this instance, they were interpreting user data, and user data was flowing to one of these places where they were running or interpreting a string as OGNL, and then allowing a user to effectively run any code they want on the machine. On the 12th of May, someone else found an RCE, a different RCE in Apache Struts that interpreted user data as OGNL. On the 20th of June 2016, someone else found an RCE in Apache Struts that interpreted user data as OGNL. On the 19th of March, another RCE in Apache Struts via OGNL. And on the 22nd of September 2017, and on the 24th of September 2018. And what you'll see here is the same mistake being made over and over again in different parts of the code base, where user data is being interpreted in a certain way that allows them to exploit the server. Now, there was only so much space on my slides, so I didn't actually include the other 10 vulnerabilities that are all of the same type, interpreting user data as OGNL. So, yeah, that's not very good. We're seeing the same sorts of mistakes being made over and over again in these projects. And it might seem like I'm making fun of these two open source projects in particular, but these stories are common across the industry, both in open source and closed source software. And it's not just small companies either. For example, Apple publish part of their source code for Mac OS and iOS called the XNU kernel. And my coworker Kevin discovered a remote code execution in a component called the packet mangler. And he reported this vulnerability to Apple with a POC exploit. They fixed the vulnerability, pushed out an update, and when they later published the source code for that version, Kevin discovered that there was still a bug in the exact same block of source code that they patched. So he sent them a new exploit that triggered a very similar vulnerability. And then Apple then later fixed that one again. So they ended up with 2 CVEs for the price of 1. So what do we do about this? How do we solve this? If these same sorts of mistakes are being made over and over and over again across many different software projects, could we potentially use this information of a new vulnerability as an opportunity instead? So once you've found the root cause, you can ask yourself the question, at that point, before you push out a patch or anything else, is there a possibility that a similar mistake may be made somewhere else in my code? There could be something architecturally that means a certain class of vulnerability is more likely to happen in your code base. For example, your use of C may increase your chances of having a memory corruption issue, or using something like Apache OGNL or a Spring's expression language might make you vulnerable to a remote code execution. So you should try and find similar mistakes, because the chances are that you will find something. Companies like Google and Microsoft, who have been doing this for a while now, call this process variant analysis. So this is a quote from a blog post from their Microsoft Security Response Center. It says, after doing root cause analysis, our next step is variant analysis, finding and investigating any variants of the vulnerability. It's important that we find all such variants and patch them simultaneously. Otherwise, we bear the risk of these being exploited in the wild. So for them, it's simply not an option not to do it. It's a stage of their vulnerability response process that happens before making details of a patch public, so that they can patch the original vulnerability and all variants simultaneously at the same time. Because if they don't do that, once they release a patch, other people will take a look at the patch, perhaps reverse engineer it, and try and find similar vulnerabilities in their code so that they can exploit it and perhaps do some malicious things with it. So how do you do variant analysis? Well, to be honest, until recently, most of the big players have been predominantly relying on lots of manual work by their security researchers or their security response teams. So you may be focusing on particularly sensitive areas of the codebase that are more likely to have vulnerabilities, or manually checking how data flows through an application using techniques like control flow analysis, data flow analysis, and checking the range that certain variables can take and ensuring that the bounds are being checked correctly. You often make use of text search tools like grep and AWK, but it can be quite tedious. Things can be made easier if you use an IDE or something else that's language aware, like SourceGraph, that allows you to use jump to definition, allows you to quickly find references to like functions and classes, and allows you to jump through the call graph. But as you can imagine, this sort of manual process has its downsides. It can be repetitive and time-consuming, particularly for large code bases. Requires lots of iterative exploration, like you might go down one code path and you realize that it doesn't really lead anywhere, so you go back up and then you go back down another path, and it can take a long, long time. Manually checking your code base is also prone to human error. So the more complex the mistake that you're checking for, the larger the code base, or the closer the deadline that you have, the more likely it is that you'll miss something. It's simply not scalable. As the size of a code base increases, manually checking for a class of vulnerability every time a new one is discovered becomes infeasible, particularly as the size of security teams is often so much smaller than the size of development teams, often just like 1 or 2%. And if you want to actually get your developers to do this as well as part of the code review process, as the number of mistakes that you're checking for increases over time, as you're coming across more and more different types of vulnerabilities, the number of things you need to check at code review also increases, which will slow down your code review to an absolute crawl. So what can you do? If variant analysis is critical for you, otherwise you bear the risk of being exploited, yet it's completely infeasible, and you don't really have the money that Microsoft or Google did to pay for like 100 or so people to be doing this for their entire job. Could we perhaps automate some of this, do you think? So what if there is a way in which we could describe mistakes that would allow us to automatically find them, allow the computer to do all the work for us, using not just the syntactic information, but including a bunch of semantic information too, things like using the call graph or control flow, data flow. We could then run it across our entire code base automatically, or run them across multiple code bases, but we could also run them continuously so that we can catch future mistakes being made that were similar to past mistakes that we know about. Well, it turns out that there are a few tools out there that allow you to do exactly this. Clang Tidy, for example, part of the Clang compiler, can be extended to write rules for C++ that take into account both syntactic and semantic information. So Mozilla, for example, have a custom set of rules that are run against every patch for Firefox submitted to Fabricator. And they're building this rule set over time, so every time they come across a new type of vulnerability, they're like, cool, can we write a Clang rule for that? And linters as well are actually starting to include more and more semantic information for their rule sets to use, particularly those on more statically typed languages. There are also a number of technologies emerging that allow you to interactively write queries over source code that include semantic information, including one solution by my company, actually. I'm not going to compare all these different technologies in this presentation, but I do want you to know that there are lots of different things you can use to make your life a lot easier doing this. And I do want to give you an idea of what such a query would look like, or such a description of a problem. So I'm going to go through an example. But if you want to talk to me afterwards about the different technologies that are available, I'm happy to chat. So this example I'm going to go through is from the same blog post that I took that quote from for the Microsoft Security Response Center earlier. So this, can we see that? It's a little blurry, but hopefully I'll be stepping through it and explaining it. So you should be able to hopefully understand. So this is some illustrative code from Chakra Core, which is Microsoft's JavaScript engine that powers Edge and a bunch of applications in Windows. So this C++ code is part of a built-in function that can be called from within JavaScript code. Now the first thing it does here is that it gets the pointer to and the size of a particular block of memory that represents a JavaScript array buffer, one that is being passed in via the arguments. And it assigns those values to the local variables pbuffer and buffer size. After that, the call to var2int may potentially run arbitrary JavaScript code because it uses the passed object's value of method to calculate its value, and you can overwrite that method in the JavaScript code. And you could, for example, make that method free the buffer, and then when the code returns, pbuffer would be a dangling pointer. So at this point, pbuffer is a dangling pointer, and buffer size refers to the size that the array buffer used to be, but it doesn't exist anymore. Then, when we later try to perform an operation on the array, using these two variables, we encounter a memory corruption vulnerability. And this is more or less what the JavaScript exploit would look like. Here you can see that they're replacing the value of method with a function that runs their own code, which triggers the vulnerability. So Microsoft assessed this vulnerability as critical. It could potentially allow arbitrary code execution in the JavaScript engine, which is pretty bad. It's about as bad an exploit as you can get on a web browser. And Microsoft wanted to know whether they had any similar mistakes to this anywhere else in the Chakra code. So they wrote a query that described the pattern of assigning the pointer to an array buffer to a variable, then calling back into JavaScript before using the pointer. So this is what the query looked like. I've modified it a little bit here so it'll fit onto one slide, and if you're having difficulty reading it, I can show it to you after the presentation as well. But for anyone who's used a database query language like SQL, there'll be a few similar, familiar concepts here. The first thing is we've got a from clause here that lists the relationships or the relations we're interested in looking at. In this case, we're looking at variables, accesses to array buffer pointers, function calls, and accesses to variables, which is either a read or a write. Where lists some conditions that need to be satisfied, and select lists the columns that we want to output. So jumping into the where condition, this line ensures that the pointer assignment and variable use are talking about the same variable. So here, in making sure that the definition and use and v are all talking about the same variable, which in this case is pbuffer. This next line is a little bit more complex. It ensures that the function call might potentially execute JavaScript code. Now, rather than enumerating every single function that could possibly execute JavaScript code in the Chakra codebase, of which there are many, I'm sure you can imagine, the security researchers knew that any code that calls back into JavaScript may eventually call this function method call to primitive. So what they have expressed here is that call might, at some point in the call graph, call this method call to primitive function. So it might call it directly, or it might call a function that calls it, or it might call a function that calls another function that calls it, and so on. So yeah, this is the function that refers to. Then this line effectively says that the call to JavaScript happens after we assign the pointer. So first we have a pbuffer assignment, and then we make the call. And then this next line says that the usage of the pointer happens after we go back into JavaScript code. So we first make that call, and then we use it. Now in the blog post, Stephen Hunter, the researcher that was writing this query and doing the research, said that in addition to finding the original vulnerability, this query found 4 additional variants that they also assessed being critical within the Chakra codebase. So that example was very specific to the Chakra codebase, but there are many kinds of mistakes that are a lot more general that will just apply across potentially a whole, anyone that uses a particular programming language. For example, there might be a misuse of a language feature, or mistakes that are commonly made with a certain type of API. And in those cases, you can actually go one step further and share your queries and checks with the world, and open source your queries, open source your Clang tidy checks, etc. And I'm going to go through an example of when this happened. Yep, I had some things there as well. So raise your hands if you've heard of zip slip. One person. Cool. That means I get to explain it. So like all core vulnerabilities, this one had a logo. And it was discovered by the researchers at SNCC. And it takes advantage of the way that zip files are structured. So you might think that a zip file contains a directory structure with parent nodes, etc., that details exactly what's inside the zip file. It's actually a lot simpler than that. A zip file is just a list of entries where each entry has a path, which is a string, which might include slashes, which then is how you know that something is in a directory. It's not actually stored as a graph inside a zip file, it's just a list of strings. And then, of course, you have the file contents and the metadata as well. So what this means is that you could put a string in a zip file that contains these path traversal components. And what happens in a lot of programs that are trying to unzip zip files is they'll just concatenate a string like this onto their target directory. And then they will then unzip files outside of their target directory. And you could potentially overwrite files you didn't mean to. Say if you're running one of these programs as root, and there was a file that was ... etc. cron tab, then you would be able to inject on the server some scripts that would run when you chose to. And there would be no indication that this has happened. And it's pretty bad. Now this turned out that it was a very widespread mistake that's made in pretty much every programming language. Any programming language you might want to be able to write an unzipping method, you're might be vulnerable to this. And here's an example of what the code looked like. So this is some Java code that does some unzipping. And this line in particular is the problematic one. So you take the name, which is the path of the zip entry, and you add it to the end of this destination dir, which is just a file somewhere on your computer. And if it's got .. in it, it could be extracted anywhere. Now, to fix this is relatively simple. You just need to check that once you've joined the paths together and you normalize it, that it's still within the destination directory. In most programming languages, this will be about 1 or 2 lines to check, so there's really no excuse not to do this. Even if you know what the contents of the zip file are, you really should do this. So when SNCC announced this vulnerability, they actually put in a great deal of effort to try and find as many of these as possible and let the maintainers of those projects know, because the repercussions were quite large. And they had, maybe there were 20 or 30 or so projects that they reached out to, and they all addressed this issue. But they obviously couldn't find everything everywhere because it's very difficult to do that sort of analysis on a wide scale. So when they announced this, Microsoft wanted to know if they were making the mistake internally with any of their code. So they wrote a query, effectively like the last one, that searched for this pattern in C#. And they effectively looked for data that flows from a zip file entry to an I/O operation without any sanitization along the way. They ran it across their code, found a bunch of vulnerabilities, but after they did that, they open sourced this query so that other people could also run it against their code to see if they were making that same mistake, which was really, really cool of them. So I think I've gone over like the power of the sort of thing that you can find with variant analysis. There's a good few examples of what happens when you don't do it, such as the examples at the start. But how would you actually take variant analysis and fit it into your workflow if you're a development organization? So let's assume that you already have a workflow in place to respond to vulnerabilities that you may have found either internally or externally. It might look something like this. You find a new security bug, maybe get it through your bug bounty or through pen testing or something. You diagnose it to find its root cause. You fix the bug, and then you push out a fix to your users. So the natural place for this to fit in would be as additional steps that follow the root cause diagnosis. So after you've worked out what's going on, this is where you would then do variant analysis. So, or automated variant analysis. You would then describe the mistake as a Clang rule or using any of the other tools available. You would see what results you get. You would probably get a few false positives because there might be some things you didn't take into account or some ways that data sanitized or some checks that you haven't written in. So you then refine your query until you've reduced the set of results down to a small enough number that you can then manually go through them and see what's there. You'll probably find a few vulnerabilities that you didn't find that were other than the initial one. So now at this point, you can fix those as well and deploy a fix to all your users that includes not just the original vulnerability, but all of the variants, which is effectively what Microsoft do and Google for their process. Now beyond that, now that the query is written, or now that the description of your mistake is written, you can run it on a regular basis, continuously monitoring to see whether anyone accidentally tries to reintroduce a problem that you're very familiar with, because that will happen. And you could potentially even integrate it with your code review so that, or have it as a nightly build or something and fix these bugs before they're merged back into your code base. Now beyond that, going one step further, before I say that though, this is effectively what Mozilla are doing in that screenshot I showed you earlier with their Clang tidy. So whenever anyone submits code, they have a bot that runs all their results. If it finds anything, it posts them and you can address it before the code is merged. So the final steps beyond this to sort of really go the extra mile would be open sourcing the checks that you've written so that other security teams or other developers from outside your organization can benefit from it. And going one step further, you can then also use the knowledge of other security teams from outside your organization or outside your group of maintainers and run those checks on your repository as well to take advantage of that knowledge. So not everyone in here, I'm sure, are developers or part of a developer workflow. So what happens if you're one of those people and maybe you don't have a vulnerability response process? So you might be part of a small startup, or you might be working on an open source project, maybe just as a maintainer. Well, the first thing to understand is that sooner or later, if you're working on software at all, you may very well be faced with a vulnerability that you need to deal with. And it would be good if you had an idea of how to go about dealing with that situation. But in the meantime, if there's any code that you're in charge of, I would highly recommend making some sort of automated checks that are like freely available for you to use and running them on your code. So what about if you're not involved in software development, but you're just involved in vulnerability discovery? Maybe you're part of some bug bounty programs. Maybe you just like breaking things so that other people suffer. So variant analysis can also be useful to you as well. So at the start of the presentation, I mentioned two of my coworkers, Mo and Kev, that have found those vulnerabilities. They're actually part of my company's security research team and about 80% of the vulnerabilities they find using variant analysis. So they know, like, they'll look at an open source project and like, cool, what mistakes has this project made before? And they'll pick out one and like, all right, let's try and write a query for that. And they run the query and see if there are any more results still. And most of the time, there are still results. So then they can report those vulnerabilities and get a bunch of CVEs. Most recently, one of our researchers found a vulnerability in U-boot and created a query for it and found 13 in total of the same mistake elsewhere throughout U-boot. So yeah, instead of finding just one vulnerability, find 4 or 5 or 6 and get all of those CVEs. There's still like so much low-hanging fruit left. So many projects are still making the same mistakes over and over again that they made in the past. So there's plenty of opportunity for everyone. So I'm getting close to the end. I've actually ran through this pretty quick. But there's a couple of things I want to talk about. Firstly, I want to say a few things that variant analysis is not. So it is not a replacement for good security architecture or a way to avoid doing large refactors. If, for example, you're coming across a whole bunch of memory corruption issues in your application, maybe still consider migrating to Rust instead of C. If you're using expression languages and you're getting lots of vulnerabilities there, maybe stop using those. Maybe if you're getting a lot of SQL injections, use auto-escaping database libraries. It's not a replacement for, or it's not an excuse not to improve the security of your application. You should go ahead and do that anyway. It is not a replacement for exploit mitigation. Stuff like address space layout randomization or stack canaries are still super useful and very important to prevent at least the harm that you can do when vulnerabilities are found. It is not a replacement for other security processes that are also very important. Fuzzing, for example, it actually complements it very well. You might find a bug through fuzzing. You look at the vulnerability, you look at the root cause, describe a mistake for it, and then instead of fuzzing resulting in one vulnerability, fuzzing and variant analysis has resulted in 5 or 6 or 10 vulnerabilities. It's not a replacement for doing vulnerability disclosure or bug bounties. They're also both very important and, in fact, can be a good source at the start for you to then do variant analysis. It's not a replacement for audits or pen testing or red teaming or writing unit tests or doing dependency monitoring. All of those are still super crucial, and it doesn't replace any of those. And the last thing, it is not something that automatically fixes bugs for you. It just finds them, and it's a process. So how you go about actually fixing vulnerabilities is still down to you or the people maintaining the code. So to recap, variant analysis is relevant to you if you either develop your own software or you do security research, at least white box security research. And if you have your own software, you probably should be doing variant analysis, otherwise you might be leaving yourself exposed. And if you are a security researcher, you can take advantage of those that aren't doing variant analysis to find lots of bugs in their code, because there are a lot. If you are doing variant analysis and finding queries for new types of vulnerabilities, share those queries with other people so that other people can secure their own code. That's very important. And also, use the knowledge that other people are doing and sharing, and use all the security tools and checks that are being made freely available, because there's lots happening every day. And then variant analysis isn't a once-off process when you get a vulnerability. Like I said, someone can always reintroduce a mistake in the future that's similar to ones they've done in the past, and you want to be able to prevent and check against that as well. So run them continuously. And VA, like variant analysis, will complement existing security practices. You can take your knowledge from fuzzing and from other things and then do VA on that, and then find even more vulnerabilities and lock down and prevent further mistakes. All right, that's all I have. Thank you. Yep, questions?
It works better when you turn it on. Thank you. I have one question. You have a query language and you have an engine. I have a couple of things. First, how can we use this in our projects? Second on, how can we improve on the engine? So is this open source? Is this closed source? Is this, where are we at that?
Parts of it are open source and part of it's a closed source. So there are all of the checks that we provide and all of the base libraries are all open source and are being contributed to by 4 or 5 different organizations, including Microsoft Security Research and Mozilla as well, and they're all submitting things to that. So that is open source. The actual engine that runs the query is currently closed source, but we're thinking about what we want to do with that in the future. As far as being able to use it, open source projects are allowed to use it for free. So if anyone has open source stuff, they can just go ahead and use it. Yeah, does that answer your question fully?
Okay, I'll bug you later on for the rest of the details.
Cool. But there are lots of there are similar projects that are existing that have different licensing models by different organizations and companies. So, yeah. Cool. Anything else? Cool. All right. Oh, yeah.
So you've presented us with the tool that the company you work for has built with some open source parts. How does it compare to purely open source tools like linters, like SonarQube, etc., etc.?
Cool. So the main difference over, so let's take linters for example. So linters typically focus mostly on syntactic checks. So, and as a result, they often run very fast. So you'll take a linter, you'll feed it a file, it'll run some checks on that. Linters don't typically do much like cross-file checks or things like being able to track data flow throughout an entire application, because doing that just doesn't really, you can't really do that in a quick enough turnaround time that linters are expected to run. They are starting to improve on that in terms of getting some more at least local semantic information, such as knowing, like getting variable references and stuff like that. But linters are still you wouldn't be able to do like global data flow throughout your entire application for that. So stuff like SQL injections, you might be able to find some, but not all of them. Applications like SonarQube, I can't remember exactly how SonarQube compares, but a lot of the existing or open source things, stuff like find bugs, and I believe they mostly have a built-in set of rules. So you can't really do the investigation without modifying the code and then recompiling it and then going and actually it's like a long turnaround time to do for variant analysis. I think the best solution for that would be Clang tidy. You still need to set up a few scripts and stuff to do like recompiling and rerunning it and stuff for you, but that's getting closer and closer. There are also a couple of other open source tools, I can't remember the names of, that are doing more graph-based, like call graphs and stuff like that, and they're definitely getting a lot closer and stuff as well. So the difference is decreasing.
Okay, thank you.
Yeah.
How do you know that some part of your software has just too many bugs and it's time to not just patch them but to change the architecture? How do you know that that's the point?
It's a feeling. It's probably, you might measure it by realizing that you're spending 80-90% of your time patching and dealing with problems as they come up rather than actually improving the application. I think that will happen for any sort of like architectural flaw, any sort of code smell. It doesn't necessarily need to be vulnerabilities, but the more time that you're spending dealing with problems rather than actually working on developing new features or stuff like that, that's a good indicator that you're due for a refactoring. So the more vulnerable, like if you're spending 50-60% of your time just addressing vulnerability reports as they're coming in constantly, then you've probably got a big problem that you need to fix, I would say. Cool. All right, well, I'll be around for the whole weekend, so if you have any more questions, feel free to come find me. Yeah, thank you.